We stopped yesterday and we were talking about one of the simplest problem in combustion, which is determining the propagation speed of a planar flame and under adiabatic conditions. And this is, as I said, the simplest problem that you can think of in premixed combustion. And the mathematical problem is written here, again, for the simplest situation in which there is only one deficient component. In other words, the mixture is either lean or rich. And I'm going to tell you later the result for a stoichiometric mixture or one that ranges from lean to rich. But at the moment, for simplicity, let's look at this problem. So we have the conservation of energy, the species Y, which is consumed, and then the reaction terminate. And on the right-hand side, the reaction rate expressed in this form, where beta was the Zeldovich number. Essentially, it's a measure of the activation energy. This is the Lewis number, and Q was the heat release. And we kept the reaction order general to be N, and the boundary conditions are such that far to the left, where the mixture is coming towards, we are in a frame of reference attached to the flame. So the flame is located in the vicinity of x equal to 0. The far to the left, the temperature is known, is the unburned temperature. Everything is made dimensionless here. The mass fraction is known. And far to the right, the temperature we found that must be the adiabatic flame temperature, TA, and everything is consumed. And so this is, as I said, the simplest problem, and yet an exact solution is not possible. This is, for example, in contrast of fluid mechanics, where we know many exact solutions of simple problem, like flow in a pipe or Stokes problem, and so on and so forth. So anyway, so we attempted to solve this in the limit of large activation energy, and I described to you the general idea. And we were able to obtain an expression for the laminar flame speed in that limit, namely in the limit when beta is large, which is a representative usually of combustion system. Usually the activation energy is large, otherwise combustible material will explode or blow up immediately as you store them. And we have seen yesterday how sensitive the reaction rate is to temperature from unburned to the adiabatic temperature. So this is the expression. It's a nice analytical form. And I want to just spend a little bit of time to understand what it displays, or what does it say. This is the adiabatic flame temperature that we have seen before, and this is a measure of the flame thickness, basically a diffusion length, but it's a measure of the flame thickness, and we are going to comment on this in a little bit. Pay attention that the laminar flame speed depend on the expansion rate, which is the ratio of the density unburned to burn or burn to unburned. It depends also on the thermal diffusivity of the mixture, if you like here, but also the Lewis number. It depends on the molecular diffusivity of the species that is diffusing. In this case, it's the deficient reactant. It depends very strongly on the adiabatic temperature because this exponential is probably one of the most influential factor in this expression. But we're going to see that all these things matter. So we're going to go through this in a second. The first thing I want to show you is, I discussed that yesterday already, and I'll comment about it later again, but this is what I wanted to show you. We have derived an approximation which is valid for large beta, and we said that typically beta is around 10. This graph shows you the ratio of the laminar flame speed if it's computed numerically, okay, solving the mathematical problem that I posed before numerically relative to the value obtained, or this formula obtained from the asymptotic case. And I think this was done for n equal to 1. And I don't know why I said sigma equal to 6. I don't think this is relevant, but maybe it was needed in the computation. I'm not sure.
What sigma was.
Oh, sigma is the ratio. Absolutely, I didn't say that. For me, it's clear, but sigma is the ratio of the density of the unburned gas to the burned gas. And I just want to tell you that it was not a trivial matter to prepare all these notes, particularly because I have tried very hard to be consistent with all my notation. And they are, I would argue, probably 99.8% consistent. So sigma is rho u divided by rho b. Anyway, 5, 6, 8 is approximately what you have in combustion system, because from the equation of state, this is the same as TA over TU. And typically you have, say, a adiabatic temperature of 1800 Kelvin. You have unburned gas room temperature, say 300, so here is 6. And of course, it varies a little bit from there. So anyway, I don't think that it's important if we did use in the calculation this value. I think numerically you needed to specify that. So anyway, the idea is that, of course, the approximation becomes better and better the larger beta is. And so this ratio should tend to 1 as beta becomes extremely large or goes to infinity, which it does. In particular, the different curves here represent solution for different Lewis number. You see, the mathematical problem depend on a couple of parameters that you have to specify. One of them is a Lewis number, so that's why it's specified here. And the other thing, I think it's the adiabatic temperature, and so that's why I chose sigma, which correspond to what is this value here. So anyway, it also shows you that for the value 10, which is typical what we have as the Zeldovich number for hydrocarbon mixture. The approximation is between 5 to 10%, which is pretty good. But the big advantage really of an analytical formula is that you can understand from it the different behavior of different parameters. So we're going to go through this, as I said, but there are a few comments that I am making here. The first one is, if we were to generalize this expression for a mixture which is not necessarily lean, then there is this additional factor that show up, S. S stands for maybe stoichiometric effect, and this is what the difference between a lean and a rich mixture would be. When phi equal to 1, the two collapse to the same expression. And when phi is sufficiently less than 1 or sufficiently larger than 1, this expression, the S goes to 1, and the expression collapses to the one that I have previously derived. So everything here is consistent. In particular, when phi equal to 1, this is the expression you get. You see the difference between what we had before here. Is that this one depended only on one Lewis number, which is the Lewis number of the deficient component in the mixture, and now it depends on both Lewis number of the fuel and oxidizer. Also, the difference is there is a beta cube as opposed to a beta square in the previous relation, and this is due to the fact that in the reaction zone, both the fuel and the oxidizer are both consumed, and everyone contribute a beta minus 1 factor to the expression. So this is one of the generalization. The next thing is I want to spend time and talk about the different effect that you can see from this expression. And in particular, I'm rolling it back just because I want to tell you the focus. I will focus on just most of the cases on the expression with n equal to 1, just for simplicity, but it doesn't change much in the discussion. N equal to 1, by the way, gamma of 2 is just 1, and gamma of 2 is 1 factorial, which is 1, and so is just a number here. For other n, it's slightly bigger, but it doesn't change much. Okay, so here is the first thing, is that the flame speed, as I mentioned earlier, depend very strongly on the adiabatic temperature due to this factor. Remember that it appears in the exponential, so small changes in the flame temperature make a big change in the flame speed. And indeed, you will see, okay, so the first comment is not about the big changes, that will come in a minute. The comment here is that there is some correlation between where the adiabatic temperature is maximum and where the flame speed is maximum in general. And that you can see for the methane air flame, that the speed, this is the flame speed measurement as a function of equivalence ratio, and it peaks around 1. Remember, we said that the flame temperature peaks around 1. But this is, you have to be careful, because some of the factors that stand in front of the exponential can change this correlation, and we're going to see in a minute how it does that. Okay, so this is the first comment. The second comment is that the flame thickness, since the flame speed appear in the denominator, have exactly the opposite trend. So the flame will be thinner when the equivalence ratio is 1, and will be otherwise thicker when you go towards lean or rich limits. Okay, so it just have the opposite trend than the flame speed. This are again measurement taken from a quite a relatively old paper in 1970, but I'm sure you can find the data more up to date in other references. Okay, here is the dependence of the flame temperature on the heat release. Now, where does the heat release appear? Well, remember, the heat release doesn't seem to appear explicitly here, but it does through the adiabatic temperature. The adiabatic temperature is, roughly speaking, the cold temperature plus the heat release. So you increase the heat release, you increase the adiabatic temperature, you increase this factor, right? So the flame propagates faster. That's what you see here. If you compare methane, ethane, and propane, the heat release is almost doubled from one to the next to the third, and the flame speed increases from the circles, which is methane, to the filled diamonds, which is the ethane, to the open diamonds, which is the propane. Okay? On the other hand, butane, pentane, hexane, heptane, the heat release increases, but relatively in small percentage one to another, and you see that the flame speed doesn't change by very much from one to another. So the idea was here to illustrate the dependence of the flame speed on the heat release, right? It makes sense that more heat released, flame propagate faster, and that's indeed exhibited in this relation. Okay, the next example here shows three species, or show the show the result of a methane air flame, but where the dilution has changed. All mixture have the same heat release, but some of them, but this one, they are diluted in argon, nitrogen, and what's the third one? And helium, right? Now, argon and nitrogen, so we see that the heat, well, it's the same mixture, so it's the same fuel, so it has the same heat release, but since argon and nitrogen have the same thermal diffusivity, as we see here, approximately the same. In contrast, the helium has a much larger thermal diffusivity. So the thermal diffusivity affects the adiabatic temperature, and therefore right. So the flame temperature of the helium mixture is similar to that of the argon mixture, but is much higher than the what's the third one? Than the nitrogen, due to the higher thermal diffusivity of helium. Did I explain that right or not? Probably not. The idea is that this factor, which is the thermal diffusivity, could affect significantly the flame speed. And so what you will see is that in a mixture where the diluent is helium, where the thermal diffusivity is 1.6, so it's like 10 by a factor of 10 bigger than the other, you would expect a higher flame temperature, which it is, right? Okay, compared to the other two, despite the fact that the heat release is the same for all three. Yeah, okay, now I think I did it right. Okay, so the next one is to show you the effect of the Lewis number. So remember that we had the Lewis number in the expression in the denominator, but they were raised to the power -1. So really they appear in the expression as such, square root of the product of the Lewis number. Now for methane air, methane, the Lewis number of the fuel is approximately 1. Methane is not a very heavy and not very light fuel, and so it's the Lewis number typically around 1. And so you see that the temperature, the adiabatic temperature and the flame speed, the adiabatic temperature was computed, the flame speed was measured in this graph. It's taken from Ed Law's book. The two are quite correlated. In contrast, for hydrogen, well, you see, for hydrogen is a light fuel, so in the lean limit, right, being the deficient component, it counts a lot, and the Lewis number is very small. In contrast, in a rich mixture, the deficient component is the oxidizer, and the oxidizer has a larger Lewis number. So you see that the correlation is not the same as in the adiabatic temperature. Here it lags, and here is a little larger. And that comes from the square root factor of Lewis number of fuel or Lewis number of oxidizer. Okay, the next one is the dependence on the pressure. I just want very quickly, to bring in one of those expressions. Remember that there is here a dependence on the density square, okay? And so, that's where the pressure dependence show up. So basically, it was, but there is a dependence on n as well. Let's see, where it come from? Oh, this is for n equal to 1. Oh, here it is. So the general expression, note that have a density to the power n, right? Okay, this is dimensionless, but when you make it dimensional, it's still, it will be a density to power n, square root n to the 1/2. So this is the way where pressure come in, okay? So it's rho b to the n over 2, and it's divided by rho u due to the non-dimensionalization. So essentially, it's proportional to the pressure to n over 2 minus 1. N over 2 come from the numerator, and minus 1 come from the denominator, because from the equation of state, P is proportional to rho, right? And so, for basically for all n, for n equal to 2, the flame speed will be independent of pressure, and for n less than 2, it would usually be a decreasing function of pressure. Now, typically, the reaction order is less than 2 because, roughly speaking, the reaction order is the number of molecules that collide to undergo a chemical reaction. And so number larger than 2, meaning that more than 3 molecules, the chance that 3 collide exactly in the right way to produce a chemical reaction is usually small. This is a very rough hand waving, but basically the numbers are usually less than 2, which indicate that in most cases what you will see is the dependence on speed on pressure is a decreasing function. And as you will see here for numerous fuels, methane and some others. Okay, what else I say? Oh, now another thing is here, the flame thickness. The flame thickness now, okay, it's lambda divided by rho u times SL. So the SL gives you a P to the n over 2 minus 1, but it's in the denominator, so it's going to be 1 minus n over 2. And you're going to lose the 1 due to the rho u, which is also proportional to P. Therefore, the dependence on pressure is always P to the minus n over 2. In other words, as you increase the pressure, flame thickness always become thinner, okay? Independent of n. So those are important results that you see immediately come out from the simple expression, and so it's very useful. I think this is the last transparency except of this one, which is a summary of what we learned from the asymptotic analysis apart from the simple expression that we got for the flame speed. What did we learn? We learned that the reaction is essentially concentrated near a sheet or a boundary layer, a very thin region, where the fuel, the mass fraction and the temperature is continuous, right? That's the first statement, that there is a relation between the flux of fuel diffusing towards the reaction and the fluxes of heat conducted away from the reaction, and the relation comes from the conservation laws. And finally, the detailed structure of this boundary layer gave us exactly the right flux that is needed for the fuel to be completely consumed, and the flux is expressed here. It depends on the diffusivity, depends on the reaction rate constant, and it is a function of the Arrhenius function with a dependence on the adiabatic temperature. And the 2 here, of course, is due to the square root of the expression that we obtained. So, and by the way, this is equivalent, right? The right-hand side is equivalent to rho u SL YU, which is the flux at the speed SL, okay? In other words, I could have taken the expression that I derived before and substituted here and show that this is SL. It's just an obvious statement. Okay, so the next thing I would like to do, which is in the next lecture, is to slightly generalize this statement. So suppose that you have a flame which is not flat, as we did before, slightly curved. So here is the picture. The flame is slightly curved. Well, if it's not highly curved, in other words, the curvature is not too, if the curvature is not, if the radius of curvature is large or the curvature is not too small, curvature is usually the opposite than radius of curvature. So I hesitated to say it right. So if that's the case, then locally the flame can be seen as almost flat. As a result of this, if you look at this little square blue box, which is the reaction zone of this flame, then we can write the previous expressions that we did, okay, with two exceptions. One is that the direction is not x, but now is the normal to the surface. And the second one is that instead of in the expression that I before derived, namely the flux of fuel towards the reaction zone that depended on the adiabatic temperature, now I'm going to generalize this to the flame temperature, because once the flame is curved, the flame temperature is no longer necessarily the adiabatic temperature. It can be something different, or it will differ from the adiabatic temperature. And so that's the two generalization. Now, it seems like it's ad hoc, but it's not. This has been derived systematically by treating the reaction zone as a boundary layer with the right curvature, and the equation were derived in that way. And so there is a generalization of this, but the mathematics is too involved, and I think that this illustrates the idea without dwelling into the detail. One more thing that we are going to just do in this expression. Remember that this expression, when this T was TA, was exactly the flux, so it was rho u SL times YU. So if I just multiply and divide by this factor e to the e over 2r TA, then the expression with the minus is SL, and the rest is just that deviation. In other words, what I'm saying is that when the flame is slightly curved, what will be important here in the exponential is the deviation of the flame temperature, the actual flame temperature, from the adiabatic temperature. Okay? And those small deviation, we will see, make quite a bit of an effect on the flame. Okay, so this is the generalization, and the first, here is what I just told you in words. If I multiply and divide by the same factor, right, this part is the flame speed, and the rest is the deviation. So I just had a slide for it. Okay, good. As I said, this was derived rigorously. It requires some other detail, but it's not crucial. The first example that I want to look at is that a flame, a planar flame, on top of a burner, a porous plug burner, a flat flame in a porous plug burner. By the way, to obtain experimentally a flat flame without a burner, let's say a freely, if you bring your mixture from a large tube and you ignite it, it's very, very difficult to obtain a flat flame experimentally. Nevertheless, I will show you later that it was done in Marseille some years ago, of course, with all kind of tricks to ensure that there is no disturbances from the surrounding and from the region above and so on. And I don't know all the details, but I know that this was performed, and I'll show you a picture of it. But in general, you can create a flat flame over a porous plug burner. Now, the first question is, what's the role of the burner and of the plug? And so, by the way, this is just a schematic, and in fact, this is what it looks in reality. It's taken from the Makina flat flame burner website or whatever it is. So the plug serves as, first of all, as a heat sink. It extracts, or it takes heat from the flame, the heat conducted to the plug. And what is normally done to maintain the temperature constant is to extract the heat through some water cooling coils. So there are water and cooling coils here in the plug that, which are here. They serve to cool off or to extract the heat and to retain the incoming temperature to be constant, to be, let's say, TU. But the plug also serves another thing, and it serves also to prevent the product to diffuse backward into the incoming mixture, so the plug allow only for the flow to go only in one direction. Okay, so now we want to set up the difference, or what's the difference now in this problem compared to what we have done before. It's primarily in the boundary condition. So the boundary condition are written here, and by the way, this condition is exactly, if you want to derive it, I have shown you in the first day how you can take the conservation law, integrate them in a small control volume near an interface, which is often referred to in the literature as a pillbox argument. The idea is that you can look at a control volume which is very thin, like a pillbox. And so you use that pillbox argument. You know what is the condition of the mixture of the fuel on this side, you know on this side, and that's basically this jump relation that you obtain. So in this case, what you have is that the net flux of fuel towards the plug, which is convective and diffusive, is equal to the flux of fuel out of the plug, which is m, which is the mass flux controlled by the plug, multiplied by Yu. And the temperature due to the cooling is retained as T equal to Tu. So these are the two boundary conditions. We have two equations. If we consider, again, only a deficient species, and the mass fraction is Y, the temperature T. And so these are the equation in dimensional form. M is the constant mass flux for this one-dimensional configuration. Now, of course, you see that I have set equal to 0 the right-hand side, namely no reaction. These are the equations in the preheat zone, namely in the region up to the reaction zone. Across the reaction sheet, we have to satisfy these jump relation that we have derived before, right? The one that I told you I'm going to generalize from the planar asymptotic solution. The three relations are written here. So in that expression, Tf is the actual flame temperature, Ta is the adiabatic temperature, and everything else is known, okay? So this is the mathematical problem now to solve. Now these equations are easy to solve, again, second order constant coefficient, and so they satisfy exponential type solution, which are written here. So in particular, if you see when x equal to xf, which is the location of the reaction sheet, then e to the 0 is 1, 1 minus 1 is 0, so that's satisfied. And you can verify later that that satisfies the boundary condition that we have specified earlier at x equal to 0, which is the location of the plug. The temperature is given by this expression where you see at the flame when x is xf, this factor is 1, T is Tf, which is the flame temperature, which we don't know, right? So we still have as unknown in this problem the location of the sheet, xf, which we haven't determined yet, and the flame temperature, Tf, which we haven't determined yet. But to our disposition, we have all these jump relations that we have derived. I have only used two of them here, continuity. We still have the relation between the fluxes and the flux of the fuel required for the fuel to be completely consumed. And when you satisfy those conditions, you get two relations here. One which tells you what's the flame temperature for a given mass flow rate or mass flux. Ma is the mass flux for an adiabatic flame, which in other words, it's rho u times SL, right? Which clearly is obtained when Tf is equal to Ta, M is Ma. And the second relation gives you the location of the sheet. Of course, it depends on the flame temperature as well. So I want to plot these two expressions to understand their meaning, but let me also point out that if I have this picture here, this is roughly what you would expect the profiles are of the mass fraction and the temperature. This is not quite right because I have taken that from one of a paper that we did some time ago where we have also solved things inside the porous plug. So in principle, forget this part. I should have eliminated. The solution should start from here down. Okay, but this is a minor comment. It's not important. The main important thing I want to illustrate here is that you can also, once you have the solution, in other words, once you have this relation, you can compute the amount of heat lost to the plug, or the amount of heat conducted to the plug. It's the slope of the temperature at x equal to 0, right, or proportional to the slope. Okay, so here are the results. First of all, I rewrote the expression for the flame position or the reaction sheet position, and here I plotted that as a function of the flame temperature, Tf. Now note that this is Tf divided by Tu, which means that it's scaled with respect to the cold temperature. And not indicated on this graph is the fact that the graph is plotted for a T adiabatic equal to 6 in dimensionless form. In other words, the sigma equal to 6. Okay? Now, how do I know that? It's quite obvious, because when Tf goes to 6, or Ta, the position of xf goes to infinity. In other words, the position is far enough from the plug. If it's far enough, it doesn't know of the existence of the plug, practically speaking, and so that the flame temperature must be the adiabatic temperature. As you get closer to the plug, there will be heat losses, which, as you see here, increases, right? And the flame will reach a minimum distance and then will move back upward. In other words, the flame will never be able to reach the plug. It will always stand up at a distance away from the plug, and that distance is determined here. And here are experimental results by Ferguson and Keck, and they show the very similar behavior as we have predicted. Okay? This is a way to measure laminar flame speed. What you do, you measure the heat loss. Those are those different blue points, and you take a regression curve all the way to when the heat loss is equal to 0. The ratio of m to ma should go to 1, and that gives you the laminar flame speed, or the flux, the adiabatic flux. So it's one way of measuring experimentally the laminar flame speed. I will show you a few others that will come from the examples that I will be doing. The next problem that I want to do is what if you have heat losses in the problem? In other words, if you don't have an adiabatic system. So here is the same problem, so the mass is coming towards the region where chemical reaction occur, but you also have some heat losses. What could be heat losses? So for example, the flame is propagating in a tube, then the heat losses are, let's say, conductive losses at the walls. But of course, a flame in a tube is not necessarily one-dimensional. It's a two-dimensional problem. So I will tell you a little bit about that later. But in this version, what we are doing, we are mimicking or simplifying the heat loss to be some volumetric heat loss equivalent to what it should be to correspond to the losses at the wall. In other words, I want to maintain a one-dimensional problem, so I'm adding a term to the equation, which is a heat loss. Remember, it's not, it's a phenomenological term in principle. Okay. On the other hand, it can be a radiative losses, which is then fine. It is a volumetric type of heat loss. And I'm not going to say which, in the analysis, which kind of losses. I'm going to say just that the losses are a function of the temperature, so they can be either proportional to the temperature difference between the local temperature and the unburned temperature, or some other functional form like this for radiative losses. Okay, everything else is clear. The concentration, the mass, the temperature, the density is known far upstream. Now the mixture is moving towards the flame at a speed, but that's not the laminar flame speed, because it will be a speed that depends on the extent of loss that the flame experience. And so I called it S without the symbol SL. And far away, the y equal to 0 meaning one of those two. Probably I will be considering again a problem with a deficient component, so y will be the mass fraction of the deficient component. So yes, it is only one. Here are the equations. They are again the one-dimensional equation as before, conservation of mass, energy, the species equation, and the only addition now is this loss term minus g of t. Minus clearly because we're losing heat, this is gaining heat. The boundary condition are rho is rho u, y is yu, t is tu, but u is s. And s need to be determined. That's the speed that need to be determined. Okay. Again, I'm going to use the same idea of a reaction sheet, and I'm going to use the same simplification that I have adopted before, namely this expression for the flux of fuel into the reaction sheet. So we are solving this equation with zero condition, in other words, no reaction on the right-hand side. This is in the preheat zone before the flame, and this jump relation across the flame. Across the flame, I mean across the reaction sheet in particular. Okay, another thing that so we are going to put, first of all, the equation in dimensionless form. And the idea is we are going to use exactly the same units as we did for a planar flame, with the exception that the speed is now scaled with respect to the laminar flame speed. So little s is the ratio, little s1 meaning an adiabatic flame speed. We expect little s to be less than 1. Everything else is the same, with one addition common to make, the same meaning that this is the Zeldovich number, Q is the heat release, Tf is the flame temperature, and so on. Ta is the adiabatic temperature, and without the tilde is dimensionless, with tilde is dimensional. Dimensional Ta is here, dimensionless Ta is here. Okay. When you see the equation dimensionless form, you know that there is a beta minus 1 here. In other words, I have selectively, or I have chosen what we often call a distinguished limit in asymptotics, is a limit in which the heat release is small. And it was built up already in choosing the heat loss term appropriately, so that appear here the small parameter in front of it. Of course, first question that I'm usually asked in a classroom is, why do you consider small? Well, weight. If small is sufficient to extinguish the flame, large will clearly extinguish the flame. And so let's see what we get from here. It turned out that that's enough, otherwise I wouldn't have done that exercise. So here is the problem, and what's in here? Oh, the jump relation. Now, since I'm assuming that the heat release is small, then I expect that also the flame temperature is not going to deviate from the adiabatic temperature by much. It's also going to be small. But that's not surprising, because being in an exponential, the small deviation Tf from Ta, if it is like beta minus 1, it produces an order 1 effect. In other words, it's sufficient in that Arrhenius term to change the temperature by a little bit of the order of the reciprocal of the Zeldovich number for the speed to increase by an order 1 amount. And that's the what's hidden behind this result, or success of this result. So the flux relation here turned out to be simply Yu after the simplification. e to the phi star, and phi star is the deviation of the flame temperature from the adiabatic temperature, okay? So this is one thing. All the other jumps are straightforward. Nothing changed in them. All right. I can solve this systematically, but I can also do something which is also helpful in illustrating the answer, and this is what I'm doing here. I'm taking the combination of the two equation for temperature and species, and I'm going to integrate this equation from negative infinity up to and including the reaction zone. In other words, I'm integrating up to, if the reaction sheet is at 0, I'm integrating up to 0 plus, okay? Now remember that the sum of these two, even when you have the omega here, the omega cancel out. And so this is in some sense exact so far, okay? So when I do that integration, okay, and then I evaluate you see, because everything is written as derivative of, so it's easy to evaluate what you have here. So for example, at the 0 plus, t is tf, y is 0. So what you get is s times tf. That's the first term. At negative infinity, t is 1, and the y is yu. 1 plus qyu is exactly the adiabatic temperature. So that's exactly what you get from that term. From this integration, you get the first derivative of this. So dt dx and dy dx at negative infinity are 0 because the mixture is uniform far away. And at 0 plus, the derivative of y is 0 because there is no more fuel, right? And so there is only temperature, and so this is the gradient of the temperature in the burn side as it loses heat. So that is from the left-hand side. The right-hand side tell you that it's integration from negative infinity, which means it's a total heat loss, right? You integrate over the whole volume, it's the total heat loss. Not exactly over the entire volume, but up to and beyond the reaction zone. Okay, so that's a useful relation because since Tf minus Ta is small, like beta minus 1, and we express that as phi star, from here we get the flame temperature deviation, right? This is expected, the slope is expected to be small because the losses are not large, and so it's going to be a beta minus 1 term, but we are going to evaluate it in a minute. And the right-hand side is kept here. The Ta minus 1 factor out, or it's divided through, it appears here, but anyway. And this is the other relation that we have seen before, just to remind you where it came from. It came from here, right? Right? This is one of our, this is the right flux that is needed to consume the reactant. Okay. So now what we have is two relations. One that tell me what's the deviation of the flame temperature from the adiabatic temperature, and the second one that tells me what is the speed, S. So I have two relations for S and phi star. Those are the two unknowns that remain to be determined. I clearly need still to know what is dt dx, in other words, what's the slope in the burn gas. But for that, I have to solve the problem in the burn gas. Well, in the burn gas, I have to solve this equation with no reaction. And it's easy to see that the solution is simply a straight line proportional to x. And so it's this green line here compared to the straight line, which is the adiabatic temperature. So this is the extent of loss in the temperature in the burn gas. A priori, this is not totally satisfactory because a straight line eventually go to 0 and become negative, but I will tell you what the resolution of that is later. For now, all I need is the slope here, and that is exactly what is needed to smooth out the solution, but the smoothing out of the solution was already done yesterday, and it's the same here too. Okay. So now we have computed the dt dx at 0 plus, because here is the slope, right? It's 1 over s ta minus 1 g at ta. So that's what I have here. Those are the two relations. This is the one after substituting here the slope, and this is the top one. So these two relations were two relations for s and phi star. The second one, by the way, is integrating the loss, but that's a function of temperature, but temperature is a function of x, so it's a composite function, and it's easier to make a change of variable where z is essentially the temperature profile. So then what you have equivalently is this expression, which is easy to understand. The first one is the total loss from 1 to Ta, namely the loss of temperature or energy in the unburned gas. And then the second one is the loss at temperature Ta, which is the loss from the burned gas. And this is all divided by 1 over s. So now I have two simple expressions. One of them here say s squared phi star is QL, and the other one phi star is minus log SL squared. And when I put them together, I get an equation for S, which is the speed of the non-adiabatic flame. And of course, the speed depends on the extent of heat loss, and then if I know what G is, I can compute it. So for example, for conductive loss, I can get an analytical expression. For radiative loss, I need to perform that integral, but that's a detail. Now let's see what that plot is. By the way, the fact that it's negative here, don't be disturbed by it. The log of a number less than 1 should be negative, and so that's perfectly fine. And that's the graph. So the graph shows that when QL is 0, no losses, the speed is 1. It's the adiabatic flame speed, right? The laminar flame speed. As you increase the amount of heat loss, the speed will be smaller, 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 smaller. Come to a point here, you increase the loss, there is no solution. The non-existence of solution is interpreted as the flame cannot exist, namely must be extinguished. Now there is a second solution here in that equation, which is the dashed curve, but this is typically unstable and therefore not observed. It's also not physically logical to expect that you increase the loss and your speed will be larger, and so even on that basis it's excluded if you want. But mathematically one can prove that it's unstable and it's irrelevant. So we have a simple expression for the extent of heat loss that will kill the flame, which is given here by, in dimensionless form, by 1 over E, or about 0.37. And what we see is that the flame is getting extinguished when the speed drops by about to about 60%. Right? When it reaches about 0.6, the laminar flame speed, the flame is gone. This is the resolution that I told you earlier. Just the fact that this line, the straight line go on, it's not an acceptable solution. Well, the idea is that really that straight line is only the Taylor expansion of an exponential that decay on a much longer scale. Because the heat loss is small, it takes a long distance for the temperature to decay to the unburned temperature. And when you introduce this large scale, you obtain that indeed the solution drop as the solid green line indicates. So there is a very compact solution presented systematically and with all the detail. Let me see where we are here. This is just an example to show you that even though I wrote it here in an implicit form, if you take as an example the conductive losses, you will see that it's a simple exponential decay, and the exponential decay has beta in the denominator. Being a large number, it means that an exponential go relatively slowly, right? All right, I'm going to take a break in a minute, but I want to mention a couple of things. This is the safety lamp invented by Humphrey Davy in the 1800s, and it was used in coal mines to basically use for to have some light, but to avoid any explosion in the mine. And so what you needed is a flame that will not propagate out due to all the dust that you have in the mine that can cause an explosion. And so what was created is a metal goes around the flame, and it was sufficiently dense to create sufficiently heat loss to prevent the flame to propagate out. Okay? So this is the idea. In other words, the QL must have been larger always than QL critical. He didn't have to his disposition this formula, but he knew how to do it without it. So this is one. The second thing, we know that flame cannot propagate in very narrow tube. In other words, if you fill a tube with combustible gas and you approach a torch, if the tube is sufficiently large, a flame would propagate in. If you make the tube narrow and narrow, eventually come a certain diameter where the flame will not be able to propagate. It's known as the quenching diameter, and you can see it from the formula. The conductive heat losses in our analysis were volumetric heat losses, so it's proportional to the circumference multiplied by L, the length, right? It's a volume. And when you present QL per unit volume, which was in the equation, then you divide by, I'm sorry, I said it wrong. The volume is pi r square over L, but the circumference is where the losses, it's the walls where the losses come from. So the total loss will be the surface area divided by the volume, will be proportional to that, which is 1 over R. So when you increase Q above QL, meaning reduce R below a certain critical value, flame would extinguish. So that's also consistent with that. I want to take another couple of minutes and then we will take a break, just because it's in the same nature, and I will split before I talk about ignition. Okay, I told you that fundamentally the problem is two-dimensional if I talk about flame in a channel or a tube. So I want to show you results here of flame propagation in a two-dimensional setting, but the results are really use a constant density model. In other words, we are assuming the flow is not perturbed by the flame. It's not exactly correct, but nevertheless it illustrates the right behavior as you will see in a minute. So now what we have is a flame which is not flat, but is curved, okay? And the problem have to be therefore solved numerically. The flame propagates at some velocity u, and which is like the little s that I presented before. And there is a parameter here in this problem, which is I call delta, which is the channel width, the 2a, divided by the flame thickness, okay? So delta small will mean narrow channel, delta large, wider channel. And the loss or the heat loss parameter here is expressed only at the boundary, right, where you have conduction losses. So the gradient dt dy at the wall is some coefficient k that depends on the material of the wall, T minus Tu, Tu being the temperature of the surrounding or the unburned gas. And this k can run from 0 to infinity. When k equal to 0 means adiabatic wall, and then you expect the flame to be essentially flat. And when k goes to infinity means the walls are cold, they are held at the temperature T equal to Tu, okay? And anything in between will measure some degree of loss, of heat loss. Okay, so here are the result of the calculation. First of all, for a wide channel, delta 20, and then for a narrower channel, delta 13. So when you go to a wide channel and you start with k equal to 0, first of all, what is shown in the graph are temperature contours. In other words, contour of constant temperature, okay, isotherms. On the left. On the right, on the right, those are isotherms. On the left, those are reaction rate contour. In other words, values that omega is the same. So where omega is small, you don't see any line. And when there is a lot of reaction, you see the contours. Therefore, taking contours of constant reaction rate is a very useful way to see the shape of the reaction zone. Okay? So what you see here is when k equal to 0, no heat loss, the flame is flat and adiabatic flame, and it propagates, in fact, the velocity u equal to 1. I don't know why it's not written here, but anyway, I don't have any u in the graph, but it should have been. In the paper, you can find it. You increase the losses, k equal to 5, the flame starts curving, and you see there is some deviation of the temperatures, no longer, the isotherms are not straight line. And, but you can increase k indefinitely. In other words, you can increase up to the value t equal to tu to maintain the wall. What happened, the flame will survive, but does not survive, it's not spanning the entire channel. It survives in the center, in the middle part. And there is a dead space here. That's what the term in the literature is the distance between where the flame exists and the wall. It's called the dead space. And that dead space, we're going to comment on it in a few minutes. On the other hand, if the channel is narrower, delta equal to 13, you start with the adiabatic condition, the flame is flat, you increase, the flame starts curving, and then you reach a value of k critical, about 28.1, that's a dimensionless number, obviously. And if you try to increase k above that, there is no solution. The flame is extinguished. You cannot establish a flame under these conditions. So basically, this is the picture. When delta is small, this is like that S-curve that I showed you before. When delta is small, the flame eventually, U over SL, it's like the little s, right? It's the propagation speed relative to the laminar flame speed. Under adiabatic condition, U is 1 in all cases. Then the velocity decreases, and where it's about 60%, exactly similar, not exactly, but very similar to the theory, 60%, it's when the flame extinguishes. It's true for delta 1, 2, 4, but then when delta become large, eventually the flame can exist for any loss because the channel is sufficiently wide. It exists in the center, and these are the just summary of what you see here. Total extinction happen in narrow channel of width smaller than approximately 15 times the laminar flame thickness. The quenching diameter is about 15 times the laminar, which is not very far from what is observed experimentally. When in wider channel you have only partial extinction, namely near the wall, and the dead space that we have seen in the previous result turned out to be approximately 6 times the flame thickness, which is also in agreement with the experiment. I think that's the end of this thing, and so I will stop here. You can read this on your own. I will start after that with